Good day everyone. First, I hope you are in good health. I am Almoutazbellah Alsamawi. I am here to present you about our paper under the title Behavior of Fully Encased Composite Column under Cyclic Loads. Concrete and steel have different advantages. Concrete has high compression strength and low cost, while steel has high tensile strength, rigidity, and ductility. Composite columns are used extensively in modern buildings, especially in industrial buildings. Composite columns are divided into three types by the position and shape of steel section. The first type is fully encased composite column as shown in figure 1. The second is partially encased composite column as shown in figure 2 and 3. Lastly, concrete filled steel columns as shown in figure 4, 5, and 6. The main purpose of this study is to analyze the encased composite column and the cyclic loads, focused on the different types of steel section and different ratio of axial loads. For this purpose, a three-dimensional finite element model is developed for the columns. The finite element analysis of composite columns is carried out by using ANSYS code. The numerical model considers the elastoplasticity of materials and the nonlinearity of contact friction. Numerical modeling, we will talk about the geometrical material properties, finite element modeling, boundary conditions, and model validation. The geometric dimension of the columns proposed is 220 by 170 mm. The longitudinal reinforcement bars consist of 4 bars of 10 diameter, and the transverse reinforcement bars consist of 25 bars of 8 diameter. All the specimens have the same cross section, but the steel section is different. The figure 7 is for the specimens of HAA 120, and the figure 8 is for the specimens of IPE 120. This table shows the characteristics of both steel sections. Material properties. The steel is supposed to behave as inelastoplastic materials, defined as elastic, perfectly plastic, as shown in figure 9. Figure 10 shows stress-strain relationship of the concrete. Steel and concrete properties specified in ANSYS contain a Young's model, Poisson ratio, and yield strength. This table describes the specific properties utilized in this numerical modeling. Finite element modeling. Considering several studies reported in the literature, it was decided to choose the used finite element model solid 65 for the concrete, solid 185 for the steel section, and length 118 for the reinforcement bars of the ANSYS code. The boundary conditions are fixed at the bottom and free at the top of the column, as indicated in figure 11 and 12. Firstly, the axial load was applied at the middle of the free end column, and the horizontal load is applied with displacement using boundary conditions under different increment steps. To validate the accuracy of the numerical model for composite column described on the previous section, Two previously results published by Herbert et al. Were used to comparison purpose. As shown in figure 13 and 14, the black line is the experimental results and the blue one is the numerical results. This the difference between experimental numerical value is plus 0.66% and 0.74%. It can be found that generally a good agreement is obtained between the numerical and test results. This confirms that the present numerical model can be used with a confidence to simulate the behavior of fully uncast composite column and the cyclic load. Analysis of numerical results and discussion. From the numerical simulation, the parameters studied are axial load level, skeleton curves, dissipated energy, ductility factor, and stiffness initial are also carried out. Axial load level is defined as the ratio of the load applied to the load calculated by Eurosteel. In order to study the influence of axial load level, we chose 9 different values of axial load level, 0.1, 0.2 until 0.9, to set up models while keeping other parameters constant. Skeleton curve can get it by connecting the peak point of each cycle lateral load displacement curves. A skeleton curve is used to measure ductility, strength, and deformation capacity of specimens, and for studying an elastic cyclic response. It can be found that these columns behave likewise in the linear stage. However, there are obvious stiffness degradation difference between these curves in non-linear stage. The lateral load decreases after yielding of the specimen. It can be seen that the skeleton curve consists of 4 different stages. First, cover spilling stage. When the curve reaches 1, the concrete cover is spilling and no yielding occurs to the steel section in this stage. Second, elastic stage, from point 0 to point 2. In this stage, the load displacement curve shows nonlinear behavior and steel section are in elastic phase. As the increasing of displacement, the steel section yields at point 2. Third, elastic plastic stage, from point 2 to point 3. Stress of the steel section also increases with the increasing of displacement. Point 3 indicates the peak lateral load of the composite column. Finally, the last stage, as we can say, the peak stage is when the curve slopes from point 2 to point 4. Dissipated energy is calculated from the lateral load displacement curve as the area enclosed by the hysteretic hooks. Generally, a lower axial load level have a higher relativity of dissipated energy of specimens as shown in the table for both steel section. With increases of the axial load level, the energy of specimens tend to decrease. Ductility is used to determine the cyclic behavior and deformation capacity of structure's element. It defines as the ratio of the ultimate displacement to the yield displacement. The results in the table indicate that the first 3 columns in both steel section have a better ductility than the others due to the low axial load compared to their resistance limit durability. The stiffness initial is used to determine the ability of an element to resist deformation or deflection under an applied load. It is evident that with an increase the level of axial load, the initial stiffness degrades gradually. The initial stiffness degrades seriously when the axial load ratio increases to 0.8. Finally, conclusion. Our paper shows the responses on composite columns subjected to various axial load and horizontal cyclic loads. The results indicate that the columns with a low axial load have a low specimen energy dissipation, due to the durability of the columns is higher than the axial load applied. The axial load had a reverse effect on the ductility and energy dissipation. For better ductility and energy dissipation in the two studied specimens of fully encased composite columns, the axial load level should not exceed an upper limit value of 0.6. Beyond this limit, the composite columns are not so efficient. Several numerical simulations are necessary to give a general analytical formulation of the performance of the composite columns subjected to cyclic loads. Thank you for your attention.